The flush, we haven't really shown run because it basically flushes every 8 hours for 5 minutes. So if we sat here and wait 8 hours, this light will come on and this automatic pass light goes up. For now, we won't wait 8 hours. Pre-treat lockout only applies if you're going to put some pre-treat upstream of the system, which I don't believe you will, so you don't need to worry about that. So the alarms of note are these red lamps. These are all critical alarms, and if these alarms occur, the system will stop. The first one is the RO pump motor fault. And for some reason, this high pressure pump draws too many amps current, and the contactors and the overload inside, we already discussed, trips. This light will be illuminated. In order to get, and this pump will stop. In order to restart the system, you will have to, you can see now, because we tripped this, the valve is closing, lights are off, system stops. In order to restart the system, you'll have to go into the control panel, put the overload back in the run position, hit the reset button, and now the alarm is cleared, and the valve will open, pump will restart. The second alarm is the low-level switch in the bisulfite chemical tank. There's also a similar one for the anti-scaling tank. If these switches indicate that there's no chemical in the tank, the dosing pumps will stop. It will not stop the system, but it will stop the dosing pumps so they don't suck any chemical up, or any air up and without any liquid in the tank. Now I can simulate these by just going over and adjusting the switch and making the alarm detected. But if the level in the tank is too low, the light will come on, pump will stop. Same with the anti-scaling. Light will come on, pump will stop. The last alarm is the low inlet pressure. The switch right here, this is a pressure switch. This can be manually adjusted. It will be factory preset to approximately 10 psi, so that if the inlet pressure to the high pressure pump drops below 10 psi inlet pressure, this light will illuminate and the pump will stop to protect the pump from running without any water in it. If you get that alarm, the way to clear that, as well as the other alarm, press the reset button. Light will go out, the system will restart. This alarm is what's called the valve fault. It applies to the flush valve right here and the automatic inlet valve right here. These valves are equipped with limit switches, which indicate the position of the valve, whether it's open or closed. So right now the valve should be open. If for some reason the valve was not open, and the limit switch indicated the valve is not open, this light is illuminated. If we tell the valve to close, if we turn the system off, the valve should close. If the valve closes but doesn't close all the way, or doesn't close at all, if the limit switch doesn't indicate that the valve is in the fully closed position, same thing. We get the alarm here and the valve fault. If you do get this fault, you need to go look at the actuator for that valve and the flush valve to make sure that the limit switches are in the right position and everything's operating properly. The last alarm is the high-feed ORP alarm. As we mentioned before, we have an instrument here to measure online the ORP level of the inlet water. If for some reason this gets too high and you have the bisulfite pump on, the bisulfite pump will run. If you don't have the bisulfite pump on, or for some reason the bisulfite pump is not doing the job of reducing the ORP, after 30 minutes, this light will come on anyway. We don't want you to run the system for more than 30 minutes with too high of an ORP. To get this alarm, you need to go find out why you have such high ORP level. If the chlorine level is too high, there's some other oxidant, maybe the bisulfite is not working right. We do not want you to damage the membrane permanently by exposing them to oxidation for too long a period of time. Now that we've shown you how all the connections are made, electrical and plumbing, and we've shown you the various valves, and we've shown you the operation of the controls and instruments. Now we'll actually show you the actual operation of the equipment. So the first thing, as we mentioned before, let's turn the system on. We got the dosing pump on in auto. We got the flush in auto. The system is going to start to run. Once the system runs, first thing we want to do is adjust our flow and our total flow, concentrate flow, so that we can get the permeant flow and concentrate flow that the system is designed for. This system is designed to produce about 50 cubic meters per hour of permeant, or in GPM about 293 GPM, or, excuse me, 230 GPM of permeant with feed of about 293. So the concentrate should be about 73 GPM. So what we're going to look for here is, if it's in cubic meters, about 50 tons per hour of permeant and about 15 tons per hour concentrate. The way we do that is we adjust this throttle valve, which controls the total flow that goes into the membranes. If we close this valve, it reduces the flow in the membranes. Open the valve, it increases the flow to the membranes. Anytime we open this valve and increase the flow to the membranes, chances are we will increase our concentrate flow and increase our permeant flow because there's more water going in. But if we need to adjust the next thing we want to do is adjust the concentrate flow using this concentrate valve here. As we close this valve, that will increase the operating pressure of the system, will reduce the concentrate flow, and increase the permeant flow. If we open this valve, we'll reduce the pressure, we'll reduce the concentrate pressure, and as a result, usually increase the concentrate flow, decrease the permeant flow. So we will go back and forth and adjust these valves until we get the flows we want. The focus is on the flows. We get the flows that we want, about 50 cubic meters per hour permeant, about 15 cubic meters per hour of concentrate. When we have adjusted those valves to get the flows we want, we can look at the pressure gauges here and confirm that we have pressures that make sense. Under normal conditions, we would expect that the pre-filter inlet and outlet pressure will be in the 20 to 40 psi range. Probably higher on the inlet pressure because we'll get some pressure drop across the pre-filter. The pump will discharge in the neighborhood of 150 to 200 psi, depending on the feed TDS and the temperature of the water. I would say under normal conditions, the water is about 25 degrees C, the TDS about 500 ppm. Feed pump discharge pressure and the first array feed pressure will be about 150 psi. Depending on how we control this valve, the more we close that valve, the more we will have a difference between these two gauges. When we pinching that valve, we might have a higher discharge pressure but a lower feed pressure. The important pressure is the feed pressure to the membrane, this one right here. So we might see this around 200. We should see the feed pressure to the membrane about 150. Then we will get a little bit of a pressure drop between the first array of membranes and the second array of membranes. Maybe this would be 140, 130, if this is 150. And then the concentrate pressure, maybe this is 150, this is 130, this might be about 110, something like that. Maybe 150, 140, 130. And you should see a little bit of pressure drop across those. Then we have the permeant pressure. This system is designed for us to put a little bit of back pressure on the first array membranes so that we can balance the flow between the first array and second array. Under normal conditions, we would expect the permeant back pressure to be 20 to 30 psi, and the permeant outlet pressure, which is the permeant should be going into your atmospheric storage tank, so this pressure should be very low. The only pressure we should have here should be the frictional pressure and any vertical pressure to go out of the system, up into a tank, and travel through some pipes. So we'll have some frictional pressure. But as a rule, we like to see this less than 10 psi. Array 1, probably 25 to 30 psi. The system is equipped with a series of sample valves for measuring the TDS and other parameters, most likely TDS, but you can measure pH, turbidity, ORB, hardness, iron, any number of parameters you can measure using these sample valves. The idea is that we can test the feed water here. We have this first one is the water coming into the pre-filter at the very beginning of the system. Then we have after the pre-filter. The importance here is after the pre-filter, you can measure the turbidity to make sure that the cartridge filter and whatever other pre-treatment you have is giving you feed water to the membrane that's less than 1.0 NTU of turbidity. Then the next 7 valves correspond to the 7 membrane houses. The first 4 are the first array. Vessel 1, vessel 2, vessel 3, vessel 4 are the first array. And these 3 are vessel 1, 2, and 3 are the second array. These sample valves are very important. If for some reason you believe that there's a problem in your permeate TDS, you look at the TDS meter, you see that the permeate TDS is higher than you think. One of the first things you can do is try to find out if it's isolated, the problem with the high TDS is isolated to one pressure vessel, or if it's systemic across all pressure vessels. So what you would do is you would check each one of these sample ports for the TDS. Usually we use a handheld meter, like this one. We come over here and we open the valve and we check our TDS, and we check and compare to the next one, next one, next one. If you have one measurement that's out of range compared to all the others, it might be an indication of you might have an O-ring problem or some other mechanical problem that is allowing the feed water to contaminate the permeate. If all of them are the same, usually it's indicating that there's a membrane problem, either scaling or fouling or some other problem. But these first 4 are array 1, the next 3 for array 2. The array 1 permeate TDS is going to be lower than the array 2, always, because the array 2 is treating the concentrate from array 1. The last 2 are the concentrate out of the system and the final permeate out of the system. So the concentrate leaving the system should be approximately 4 times the TDS of the feed TDS that you measure over here. The permeate should match, if you measure it by hand, should be pretty close to the permeate shown on the TDS meter up here. These are very useful in troubleshooting and diagnostics of the system.